Just a whiteboard also?
Just whiteboard.
Great. Russian style. So
French style.
I think it's time, yes. It's 20 to 5. So it's our third seminar this year, and our second seminar in English. And I am very happy to
по расписанию. Нет, мы можем куда-нибудь уйти, если нам скажут, куда. Хорошо.
Может, тогда извините, пожалуйста. Можно на коллоквиум. А если они хотят послушать коллоквиум?
Я не говорю, что нам послушали по коллоквиуму, но если они потом перед дисциплиной программирования отчислятся,
то ну, нормально?
полноценный обмен.
Я проверю, что это программное инженерия.
right. So once again, I'm happy to.
Russian style.
So I'm happy to give the floor to Geoffrey Décrouez, who is our colleague. He well defended his PhD in Grenoble, I guess.
In Grenoble and in Melbourne.
And in Melbourne. Ah, it's
Co-tutor.
Mm-hmm.
So joint agreement between two universities.
I see. And he's a probabilist, and he will give a talk on the concept of multifractality and its applications.
Yes. Sure. Thank you. Okay. Yes, I'm going to talk about multifractal analysis, and really I want to focus on the point of view of multifractal formalism. Okay, I will explain all of that. So basically, the way it's structured, before I go through the multifractal formalism, I want to remind you or introduce the concept of box and Hausdorff dimension. Okay, which are very much needed in order to talk about multifractal analysis. So from this, I will move on to the multifractal formalism. And illustrate the procedure on some classic example. And the first example that was introduced by Mandelbrot actually in the 70s to deal with this sort of objects is multiplicative binomial cascades. Okay, so I will tell you what it is, and I will show you how this fits to the multifractal formalism. Okay, and then I will also talk about some processes which are self-similar with stationary increments. Okay, and also I will illustrate here with examples from my research. Okay, so that's the plan for today. So first, I want to let you know about box and Hausdorff dimension. Okay, so for example, if we are in RD, okay, the Euclidean space of D dimension, and if we want to cover balls, for example, okay, imagine we've got a ball of unit radius in RD. So a ball of radius R, its volume is proportional to R to the power D, right, in RD. So if you want to cover a ball of unit radius with balls of radius R, much smaller than 1, of course, you will expect that you will have this number of balls which is proportional to 1 over R to the power D because of the actual volume. Okay, so this is what you would expect. And in fact, if you illustrate this on not a ball, but let's say a box of unit length, okay, you see that you would need 4 boxes of side length a half to cover this unit box. Okay, and you would need 16 boxes of side length 1/4 to cover your unit box, and so on. So, in fact, you would need 1 on R to the D boxes of side length R to cover this unit box. Okay, so this is where this comes from. And so here we are in R2, all right? So in fact, you can see that you need 1 over R squared boxes. And so it's quite tempting to take this exponent here as a definition of the dimension. Okay, so in other words, if you've got some object A here, what you would like to is define the dimension of A to be the limit as R goes to 0, that is when we refine the covering of the log of the number of boxes needed, divided by the log of 1 on R, so minus log of R. Okay, so this is just the motivation for doing so. And this is what is known as the box dimension. In fact, it has other names, okay? It's also known, for example, as the Minkowski dimension, and so on. So anyway, I will use box dimension, and so I will use the subscript B to denote this dimension here. So this is a very practical dimension because practically, if you've got an image or a bunch of data, you can estimate its box dimension pretty easily. Because what you do is you take a bunch of coverings and you refine the covering, and if you do plot on a log-log scale, NR versus R, then the slope of this would give you an estimate of the box dimension of A. Okay, so that's the idea. Okay, another interesting fact about this thing here is the behavior of NR times R to the power S for some other exponent S. So, for example, when S equals D, the actual box dimension, you can see that the product NR times R to the power D is roughly constant. Okay? But if you're here, NR to R to the power times R to the power S, as R goes to 0, this quantity for S less than D will go to plus infinity. Okay, and in here, NR R to the S goes to 0 if S is bigger than D. Okay, so you've got this sort of transition point here that is by definition the box dimension, below which this product goes to infinity, and above which it goes to 0. Okay, so that's enough, I think, for the box dimension. But there's another dimension which is related to the box dimension, and that's the Hausdorff dimension. Okay, which allows greater flexibility, if you want, to calculate the dimension of objects. But the underlying idea is still the same. That is, we're going to cover our objects, initial object, and we're going to refine the partition, okay, to be able to compute its dimension. So, for example, if you've got a curve C, and you want to compute its length, or estimate its length. Okay, you want to find an estimate of the length of C. What you can do is you can cover this object with balls and say that the length of C is roughly equal to the sum of all the diameters of your balls. Okay? But in fact, you could have misplaced balls. Okay? For example, these ones, which are not very useful, that are covering your object in a way. So what a better estimate of the length would be to consider the best partition somehow. So you take the infimum of the sum of the Bj, such that still your curve is included in the union of the Bj. Okay, so that's...
And what is the absolute value of Bj? Is it volume?
That's the radius. Or the radius, or of course, we could say proportional to the radius, diameter,
okay.
But that's the idea. Okay. So that's one refinement, but it's not enough, because if you've got a curve which behaves like this, for example, and you cover it with this kind of ball, you can see that the ball is not really following the contour of your curve. So this estimate here is not very good. Okay, so in other words, what you need to make sure is that the radius of the ball covering your initial object is not too big. Okay, so what we're going to consider now is the infimum over the sum of the Bj, such that C is included in the union, but also such that the radius, Bj, is less than some value delta, to make sure that we are following the contour. And by analogy of what is happening in RD, we're not going to consider the sum of the Bj, but the sum of the Bj to the power D, or to the power S. Okay, which is just the analogy of the volume of a ball in Rs. And this quantity I'm going to denote it H, S, delta of, let's say, your object A. So now, what's happening is as delta becomes smaller and smaller, so when you're refining your covering, the set of possible covering is decreasing. So the infimum is increasing. Okay, so it makes sense to consider now the limit as delta goes to 0 of this quantity here. The limit can be infinite, of course. I'm not saying the limit is finite, but it makes sense to consider this limit. And this I denote it by H, subscript H, S of A. Okay, and this is the Hausdorff measure of A. Okay, we're measuring the object. And you can see now already that there is some sort of analogy with what we had before, because what we had before was NR, the number of boxes. Now we don't have NR, but we've got a sum, times R to the power S, and here we've got times the diameter to the power S. Okay, so there is a direct analogy with the box quantity dimension here, except that the boxes now do not have the same weight. Okay, the weight is given by the radius to the power S, and the radius is variable. Here the radius is fixed. Okay, so there is a difference, but anyway, there is an analogy, and you would expect, and it's the case, but just intuitively you would expect that the Hausdorff measure of A behaves in a similar way as this. Okay, and in fact, it's true. So if you have a look as a function of S, you will see that the Hausdorff measure of this set A will be plus infinity up to some critical value and 0 above this critical value. And now you will see that it makes sense to define this critical value to be the Hausdorff dimension, okay, of your set A. So, in fact, the value of the Hausdorff measure of A at this particular point can be any finite number. It can be 0 or it can be infinite. Okay? The value is not necessarily finite in this case, but we can still define the dimension of A to be the supremum of the S's such that the Hausdorff measure is infinite, or the infimum of the S's such that the Hausdorff measure is equal to 0. Okay, so
in this concrete example for this, say, reasonable curve on a plane, what will be this value?
So that's very nice, because the Hausdorff dimension and the both dimension for smooth manifold, which are subspace of Rn, will have dimension m.
So S should.
Okay, so that's very nice.
But
so there are, yes?
But if you take an innocuous example, like on a line, a set of points with coordinates 1 over n, a sequence, then with box dimension, if it's 1 over n to the power alpha, you will get a non-trivial box dimension which will be alpha dependent. With Hausdorff dimension, you will get dimension 0 as expected. So this is a final rule.
This is right. So funny things can happen actually with the box dimension. Okay, so you can have counterintuitive box dimension for some specific objects, but it turns out that it has a very practical appeal because you can compute it on real objects. This one you cannot. Okay, and in fact, you can show that the box dimension of the object always provide an upper bound for the Hausdorff dimension. Okay, so somehow you can see it as being an estimate, even if what you would really like to compute could be the Hausdorff dimension, because it really tells you about the fine structure of your object. Okay, but the box dimension gives you an upper bound. So you can have equality, but you can also have strict inequalities here. So I just want to give you maybe an example where we have equality, because you probably most likely seen this object before. That's the contour set. Okay, we have a look at the contour set. We start with a unit interval, 0, 1, and what we do is we remove the third bit. And it's an iterative procedure, so we keep repeating this. Okay, that's after the second iteration. And you can see that at iteration k, we've got 2 to the k bits, which are of length 3 to the minus k. Okay, so you can clearly cover your object with exactly 2 to the k balls, which are each of diameter 3 to the minus k. Okay, so when you do this calculation using the box dimension, you can see directly that the box dimension of A is, when you take the limit, log 2 over log 3. Which is of A, of, let's say, C, the contour set. Okay? Of course, the contour set is obtained as a limit. Okay, that's the limiting object that we're talking about here. Okay, and this makes sense because, of course, you end up with something which is between 0 and 1. It should be less than 1 because you are not as full as 0, 1, but still the object that you end up at the end is uncountable. And so you would still like to have a dimension which is bigger than 0. It's more than a set of points. And so this box dimension is really giving you this characterization that you would like to have, a number between 0 and 1. An object which is quite filling the space, but not quite as much as the original interval. Okay, and that's for the box dimension. For the Hausdorff dimension, in fact, there is a nice property of the Hausdorff dimension. If you scale your initial object by lambda, then its Hausdorff dimension measure, is given by lambda to the s times hs of A. And this makes sense intuitively, at least if you think just box dimension. If you scale your initial object in R2 by 2, the number of objects you need to cover it is multiplied by 2 squared. And the same behavior occurs for the Hausdorff measure. Okay, so you've got this sort of nice property. And so for objects like the contour set, for which you've got some sort of iterative procedure, you can see that if you measure directly the set itself, so if you compute the Hausdorff measure of the set, the contour set, it should have the same measure or if you add the measure of these 2 bits here. But this first bit here is the set itself scaled by a factor 1/3, so it's the same as hs of c on 3, and this bit as well here. And then we can use this property, so this is 1/3 to the s time plus 1/3 to the s factor of the Hausdorff measure. Okay, you can see that these two cancel, and when you solve for s, you will see that you end up again with log 2 over log 3. Okay, so that for this set at least, we've got that the box dimension is equal to the Hausdorff dimension. Okay, but it's not true in general. In general, we can have a strict upper bound. Okay, so basically that's as much as I want to tell you about box and Hausdorff dimension. But as you will see, this will become very convenient when we start talking now about the multifractal formalism. Okay, so the multifractal formalism is concerned about the geometry of of processes. Okay, we're going to look at time series, so data, signals, whatever you call them, and we're going to look at the roughness of the sample parts of these objects here, which are quite irregular as a function of time. Okay, and the way we're going to study these objects is through the multifractal formalism. So, okay. So basically, what we have is now a time series. So we've got some process. Okay. And what we want to know is about the fine structure of the process. So we're going to zoom on the process and see what is its local fluctuations around some points. So, okay. Let's take this point T here, for example. We would like to know how rough or how erratically the process fluctuates around T. So what we do is, first, we're going to remove any polynomial trend that you could have in your data. Okay, so we remove the smooth part present in your process. Okay, so what I'm going to do is I'm going to take a point U, which is in the neighborhood of T, and I'm going to compare the process at U minus the polynomial. That depends, of course, on the particular value T that we've chosen. And this is getting rid of the polynomial trend, and what is left usually is some sort of non-integral component, because the process here will not be differentiable an integer number of times. Okay, so what you're left with, roughly speaking, is U minus T to some power H of T, and this power is non-integer. And this is what we call the Holder exponent. And it gives us an idea of how rough the exponent, the process is around this point. Okay? And when you've got this kind of time series, questions that may arise, for example, is, do we have a single Holder exponent which is constant as a function of time? So do we have a unique H for all T? Or does the process convey much more rich structure in the sense that H will really vary erratically as a function of T? So multifractal analysis is interesting with these kind of questions. Okay, what is the collection of Holder exponents do we have in our time series? And it's nice to deal with theoretical objects, but we would like to answer these questions, of course, in practice. So if you've got a bunch of data, how can we estimate what are the collection of Holder exponents? And this is where the multifractal formalism is helpful. Okay, so to do this, we're going to have to be a little bit more precise in the way we define these exponents. Okay, so I'm going to denote by H of T this exponent here, but assuming that we don't have a polynomial trend. That is, this is just a constant and equal to y of t. So there is no polynomial trend. This might be a mistake if you deal with real data, okay? But there are tools using wavelets, and I'll talk about that later, so that it doesn't matter. Okay, you may have polynomial trends using wavelets, it doesn't matter. But now, as a first introduction, we assume that there is no polynomial trend, so that your singularity exponent, or Holder exponent, is defined as the lim_inf, just to make sure that everything that we define exists. Okay, the lim_inf of 1 over log of 2 epsilon, because we are looking at intervals of length 2 epsilon, of the log of the supremum of the variations in this interval. Okay, and this definition is motivated by this heuristic derivation. Okay, and again, this is nice in theory, but now if you want to do this in practice, what we need to do is some sort of approximation of h of t. So if you restrict ourselves, for example, to the interval 0, 1, what we're going to do is we're going to decompose this interval 0, 1 into a bunch of dyadic intervals. Okay, so we're going to refine this, we're going to split this in 2 bits, then in 4 bits, then 16, and so on. Okay, so that at iteration n, we've got here intervals which will be of length 2 to the minus n. And for each t, we can find an interval here that I'm going to denote I, k sub n, n, because we are at generation n. And yk of n is chosen such that here the value is kn over 2 to the n, and here it's kn plus 1 over 2 to the n. Okay, so that's the kind of notation that I'm introducing here. And once you've got this, your hkn, for this value t, is going to be 1 over log 2 to the minus n, which is the length of your interval, times the log of the supremum of what? Of y of t minus y of u for u in the interval kn over 2 to the n, kn plus 1 over 2 to the n. And in fact, this is not quite true, because what we're dealing with when we're dealing with measuring Holder exponent or dealing with concepts of box dimension or Hausdorff dimension, like we said before, we are covering our object with balls. Okay, so here what we need to do is we need to cover our object with balls, but t here can be arbitrarily close to boundary values, so that when you cover with balls, you might be a little bit outside of this interval. So to prevent problems that could arise for values of t which are very close to the end of the intervals, what we're considering is 3 times the interval. So kn minus 1 up to kn plus 2. Okay, so we're looking at the supremum of the variation of our process along an interval of length 3 times 2 to the minus n.
Excuse me, I have one question. What is lim inf? Is it just limit of infimum?
Yes, that's right. That's the way it's defined.
Okay, yes. And then why does no infimum in HKN?
It might not exist. That's why. That's just to make sure that the lim inf and the lim sup always exist. So we are sure that defining things this way, everything is well defined. But then you could introduce this h bar lim inf and the h sup, which is lim sup of epsilon, and then end up with a whole bunch of other things, okay? But I'm not considering it, but of course, we need to question this, yeah. But, okay, so this exists, and now, with this definition, in fact, for all epsilon, you can actually squeeze your interval t minus epsilon, t plus epsilon, into intervals, which into dyadic intervals, so that you can easily prove, in fact, without too much trouble, that this hkn of n converges to h of t as n goes to infinity. Okay, that's not a big deal. Okay, so this is the singularity exponent that we are interested in, and when we do the multifractal analysis, what we really care about is what we call the iso-Holder set. Why iso-Holder set? Because it's the set of t values such that your singularity exponent is equal to a fixed number, h. Okay, so basically here we are looking at the sets of t's on the real axis, such that at this value, the process has exactly the irregularity h. And for processes which are multifractal, I haven't defined them, but for processes which are very rich, usually this set of points here is a dust of points, but it's still very dense in the sense that it has a positive Hausdorff dimension. So if you look at the set here, it's usually fractal in the sense that the Hausdorff dimension of this set of points is strictly positive. Okay, so what we would like to characterize is the Hausdorff dimension of this set of points. There will be a more likely value or a value for which you're more likely to see in the process. Okay, and the bigger the set is, the larger the Hausdorff dimension will be. So this is an indicator of the geometry of the process and also about how often you will encounter this this exponent here. Okay, and if you can characterize this, that I denote by d of h, you're pretty happy because that's what the multifractal analysis is. If you have a process like this, what you would like to compute is this quantity, which is known as the multifractal spectrum, or the spectrum of singularities. It has many other names. So that's the goal. Given a process, given some data, can we try to find its multifractal spectrum? Well, again, it's going to be difficult because the data that we get is discrete. Therefore, you don't really have access to h of t. And even if you had access to h of t, then you will need to compute the Hausdorff dimension, which is, again, impractical. Okay, so this doesn't really work. So that's where the multifractal formalism comes from. We're going to end up with a bunch of inequalities like this, where here you've got a lot of information about the fine structure of your process. Here you will have information which is much more coarse about your process, but these quantities here would be easy to compute in practice with data, and this not. Okay? And the whole idea between the formalism, what mathematicians like to look at, is when we actually have equalities in this case. Okay? So that's our task here. Try to find what are these quantities here that provide upper bounds for the spectrum. Okay, so how to do this? Well, the first idea is to replace the Hausdorff dimension with the box dimension, okay? Because it provides, as we saw before, an upper bound for it. So to do this, I need to introduce some further notation, and I'm going to denote by this quantity. This quantity will count the number of intervals over which our process will increase with the right order exponent. Okay, so at step n, we want to increase with the right order exponent, which is h, up to some precision epsilon. Okay, so we are counting the number of k's, which are between 0 to 2 to the n minus 1, such that the coarse order exponent is equal to h up to some precision epsilon. And we introduce the spectrum f of h, which is equal to the limit as epsilon goes to 0 of the lim sup this time. We could consider the lim inf as well, and I would end up with a different spectrum as n goes to infinity. Of what? Well, of the log of this number, which is the number of boxes or the number of intervals that is covering the real line, divided by minus log of 2 to the minus n, okay, which is exactly the definition of the box dimension. Okay, and this quantity here is nothing else but 1 on n log in base 2 of the number n of boxes. Okay, so this is our spectrum, and I'm sure what you would expect is that this provides an upper bound for the multifractal spectrum. And in fact, it's true, and we're going to show that. I'm not going to prove everything, but maybe just to give an idea of how proofs work, I'll just show you at least this one, that indeed this spectrum, which is known as the grain spectrum or the grain-based spectrum. Is indeed an upper bound for the multifractal spectrum. Okay, so I'm going to prove this. Okay. So, what do we need? Well, we need to fix some strictly positive h and some arbitrary gamma, which is larger than f of h. And what we're going to do as well, we're going to squeeze in some strictly positive eta, such that gamma is bigger than f of h plus 2 eta. Okay, so that's what we're going to do. Okay, so first, well, how can we prove this? What's the idea behind? What we need to do is we need to find a covering of these sets of constant order exponent such that the covering has gamma Hausdorff measure which is 0. Okay, because if it's the case, remember the behavior of the Hausdorff measure, it's plus infinity here and it decreases suddenly to 0 here. So if the covering has gamma Hausdorff measure 0, straight away we can infer that the Hausdorff dimension of this set of points is less than gamma. If you're here, necessarily the Hausdorff dimension must be less than this value. And then what we do is we let gamma tend to f of h, and we have what we want. Okay, so how can we find this covering? First, it follows directly from the definition that if you take large enough, because f of h is a limb soup, then what we have is f of h plus a strictly positive quantity will always be bigger than this value here. Okay, in other words, this number of boxes will be less than 2 to the power n times f of h plus eta. Okay, so now what we want is we want to cover this. So we need to find a set of indices which have the right order exponent. Okay, so what I'm going to denote is j of m, which is the union of all the kn with n bigger than m, such that the order exponent is indeed between these two values. Okay, which means now the intervals a, k, n, for which kn is in this set, will definitely cover E of h. Okay, so that if we take the union of all of these, for all the kn in this set, of all these intervals, this indeed is a covering of these sets, because they increase with the right order exponent. Okay, so what we need to compute now is the Hausdorff measure of this. So what we need to do is we need to compute the sum over n, the sum over kn of the length of these intervals to the power gamma. Okay, so how many of these intervals do we have? By definition, here we exactly have n h epsilon of them. And what is the length of these intervals? They're all of length 2 to the minus n. So this is the sum of the number of intervals that we have times 2 to the minus n gamma. And then we can use our estimate on the number of boxes covering E of h. So this will always be less than the sum over n of 2 to the n f of h plus eta 2 to the minus n gamma, which is the sum of 2 to the minus n times gamma minus f of h minus eta. But then we're done. Why? Because the way we chose our eta is such that this quantity is bigger than eta, so that this is less than 2 to the minus n times eta. Okay, so this quantity is finite, it converges, so it goes to 0 as m goes to infinity, which means that your gamma Hausdorff measure of your covering is 0, and therefore that the Hausdorff dimension is less than gamma. And next, what you do is you let gamma tend to f of h, and you're done. Okay, so that was hard, but there is much more work to be done, because this is not practical enough what we have here. What we have so far is that d of h is less than f of h. Okay. So that's, if you want, the first interpretation of your coarse spectrum. It provides an upper bound for d of h. But there's another nice interpretation of this, which is actually maybe more insightful, is that you can interpret your f of h in large deviation terms. Why is it so? Well, okay. Consider this quantity here. Two to the n is the total number of exponents that you have. Okay? And so this is roughly equal to the proportion of exponents which are roughly equal to h. Okay, that's fraction of exponents roughly equal to h. But n counts, it counts the number of boxes, so it's a sum of indicators. Okay, so you can apply the law of large number, which tells you that basically this will converge to the probability that h of t minus h is less than some epsilon. So, if now you have your dyadic structure here, and you look at the set of Holder exponents corresponding to the process y of t. So you've got your process, and here I just have a look at the Holder exponents, hkn of n. So at this stage, it's very important to understand that these y of t are fixed in the sense that we've got a random process, but we are fixing the sample path. Okay, we just look at one observation, one realization of the sample path. So there's no randomness at this stage associated with y of t. But what we're going to do is we're going to choose at random one point here. So we are putting a uniform distribution on the sets 0, 2 to the n minus 1. So you choose a point at random, and basically this number will tell you the probability that you find an exponent which is roughly equal to this value. Okay, so that's the interpretation. And so what we have now is, from the definition of the coarse spectrum, you can see that for n large, n times f of h is roughly equal to log 2 of the number of boxes. It's just from the definition of the coarse spectrum. Okay? So that if you rearrange everything, you will see that this number divided by 2 to the n is roughly equal to 2 to the n times f of h minus 1. So remember, this gives you the probability, if you choose a point at random, to obtain a Holder exponent which is roughly equal to h. And so this, which is equal to this coefficient, this exponent f of h here, is really giving you how fast you decrease when you try to observe a Holder exponent which is not close to the most likely value. Okay, so in other words, f of h is really associated with the theory of large deviations. And it tells you that in fact this probability is decreasing at an exponential rate, whose rate is given by the value of the spectrum here. So we can use now the theory of large deviation to go a little bit further. And I'm going to use a result, a generalized form of the theory of large deviation, which is due to Gardner and Ellis. Where they deal with just very random objects, very general objects, okay, in very general sample spaces. And the result goes as follows. So, I need to define a bunch of quantities first, a bunch of numbers, an, taken to log of 2 to the n, but what's important is that an goes to infinity. I'm going to define random variables yn equal to minus n times hk of n, log of 2. And I'm going to define Pn, which is the uniform distribution on the set of indices here. Okay, and this k here is the only source of randomness. So k follows distribution Pn. Okay, so again, just to make things clear, we consider just one sample pass, so there is no randomness associated with y of t. The only randomness comes from which Holder exponents do we pick, according to this distribution here. So, now the result of Gardner and Ellis tells you that if you look at probabilities that yn over an belongs to some set A, I'm going to denote A epsilon because it will shrink towards a single point at the end. Well, this goes to minus the infimum over y in this set, A epsilon, of I of y, where I of y is the supremum over q of qy minus some other function c of q. So here we've got the Legendre transform which appear, which is quite classical when you deal with large deviation principle. Okay? And again, another thing which is quite classical when you deal with large deviation is that what you end up to deal with is the log of the moment generating function. Okay? So the c of q here is in fact the limit of Cn of q, where Cn of q is 1 of an times the log of the expected value under Pn of exponential qyn. Okay, so the log of the moment generating function. So all of these are quite classical results, but now that we're going to apply in our problem with this particular definition of an, yn, and pn. So first, note that yn over an is equals to minus hk of n. Okay, so the sets that we're going to consider for A epsilon will be of the form minus h minus epsilon, minus h plus epsilon. So that when epsilon goes to 0, this set goes to a single order exponent, the one that we want to measure. Okay, so we've got two things to compute, the left-hand side and the right-hand side here. So let's start with the left-hand side. Okay, what we have is the following. We've got 1 over an times the probability that minus hkn belongs to minus h minus epsilon minus h plus epsilon, okay, which is the same as 1 on n log in base 2 of this probability. But remember, this probability here is equal to this one under Pn. Okay, so log in base 2 of n of h epsilon divided by 2 to the n. Okay, so here you end up with a minus 1 plus, by definition, 1 on n times the log, which goes to, I should say, converge to f of h. Okay, so that's for the left-hand side. What about the right-hand side now? So for the right-hand side, we need to compute the log of the moment generating function. Okay, so we need to compute Cn of q, which is 1 over n log in base 2 of the expected value of exponential qyn. So Pn here is the uniform distribution over 2 to the n indices. So this is 1 on n, the log in base 2 of 1 over 2 to the n, times the sum of exponential q times yn, which is minus n hk log 2. Okay, so we have here a minus 1 that goes out, plus 1 on n log base 2 sum here from k equals 0 to 2 to the n minus 1 of 2 to the power minus n q hk of n. And this quantity here is a very important quantity, in fact, in multifractal theory. So we're going to give it a name. It's called the structure function, and I'm going to denote it by Sn of q. Okay, that's the structure function. And it's equal to sum of k equals 0 to 2 to the n minus 1 times 2 to the minus n q hk. And now I'm going to introduce another function, which is the partition function, which is going to be the lim, or again, to make sure that everything exists, the lim inf, as n goes to infinity, of minus 1 on n log of base in base 2 of the structure function. Okay, so these are two very important quantities, because you can see already that there are things that we can compute with real data. So as n goes to infinity, this converges to minus 1 minus tau of q with our notation. Okay, so to summarize, what do we have? We have that the left-hand side, which is minus 1 plus f of h, is equal, we've already taken the limit, to minus the infimum, okay, minus the limit as epsilon goes to 0, the infimum over y in a epsilon of the supremum over q of q y minus c of q. As epsilon goes to 0, our a epsilon shrinks to minus h. So the infimum here shrinks to minus h. So this is just the supremum over q of minus QH minus C of Q, which is the same as the infimum over Q of QH plus C of Q. Okay, so we can rearrange the terms so that now f of h is equal to the infimum over Q of QH plus 1, there is a minus 1 here, plus C of Q. But 1 plus C of Q is equal to minus tau of Q. Okay, so this is the infimum over Q of QH minus tau of Q. So what we got now is that the core spectrum can actually be computed from the Legendre transform of QH minus tau of Q, where tau is the partition function. But I didn't tell you conditions under which this holds. This is a nice result, but there are very restrictive conditions under which this holds, and in particular, one of the conditions is that C of Q is a convex function. In other words, that tau of Q is concave function. So this does not hold all the time. So what happens now when we are not under the assumption of this theorem? So what happens is we can show that in general what we have is that f of h is less than the infimum over Q. Okay, so the Legendre transform of this partition function in general is only providing an upper bound for this spectrum. Can I just know like how much time I have left? Because I'm happy to prove this, I just want to know.
Well, we're supposed to finish at 6, and it's now 20 to 6. So
20 to 6?
If.
After 20 minutes?
20 minutes left.
I'm not going to prove this.
And you're just in the very beginning.
Oh, I'm sorry. Okay, I didn't realize time was flying so fast. Okay, so far we've got these inequalities here. Okay, and this is nice, so generally we give it a name. So it's tau star of h. And, okay, I'm going to go a little bit faster. These are nice, but if you try to compute this tau of Q straight away from data, you're not going to, or from like a theoretical process, you're not going to be able to, because this is defined pathwise. What we would like to now is to define some sort of ensemble average. So what we're going to define is we're going to define a partition function and a core spectrum, which are deterministic, in the sense that now we're going to average out everything, so that the randomness in choosing the h of k does not only come from which point we pick on the real line anymore, but it comes from there, plus the randomness which is associated with the random process itself. So I'm going to define capital T of Q to be the lim in, as n goes to infinity, of minus 1 on a log 2 of the expected value of this Sn. And this expected value is taken over all the processes that we consider, okay, over the sample space omega. So this is a deterministic, is the deterministic partition function. And in fact, what we can show is that almost surely tau of Q is always bigger than T of Q, so that when you take the Legendre transform, this is less than infimum over Q of QH minus capital T of Q. Okay, that we denote by T star of H. So we're almost done now, because we have the set of inequalities that we want, and we know, for example, that here we have equality when tau is concave. So we've got some sort of indication here. And what's nice is that this T of Q or this tau of Q are easily computed on real data. Okay, so I want to illustrate now this multifractal formalism on the binomial cascade. So the binomial cascade was introduced by Mondelvo in the 70s when he was like starting to build all this fractal theory. And the idea behind that is very simple, but departs from traditional objects, mathematical objects that people were dealing with up to that point. Because people really like to deal with random walks, for example, which have an additive structure. Multiplicative cascades, by its name indicates, it has a multiplicative underlying structure. So the way it's constructed is very different from the objects that people were considering up to that time. And the idea is very simple. What we do is we consider the interval 0, 1, and we're going to measure this interval 0, 1, and we're going to give it a certain mass, initial mass m0. And then, so it's an iterative process again, we're going to split this interval 0, 1 into 2 bits, and we're going to distribute this initial mass into 2 sub-intervals. And we'll repeat this process again. Okay, so we end up with a measure here of the interval 0, 1. And we repeat this infinitely many times. Okay, so you end up with an object which has, in fact, multifractal properties in the sense that the spectrum here is very rich. It contains a whole bunch, a continuum number of order exponents in its spectrum. And so what's nice also is to see that this kind of procedure can be linked to a tree structure, because at every iteration what you end up with is a split, a dyadic split. Okay, so you've got here a binomial tree. And just to indicate, because I won't have time, but in my research what I've been considering is also what happened when you've got a random tree, for example a Galton-Watson tree. Okay, so you're just adding more randomness here. And I also consider the case where the interval 0, 1 is now split in a non-uniform kind of way. So you're messing up with the tree structure, and you're messing up as well with the subdivision of the interval. Okay? But if we place ourselves in this simple case, I would like to compute now, and I will probably finish there, the multifractal spectrum of this measure. Or, in fact, of the process m of t, which is the integral of the measure up to time t. Okay, so this process m of t is, of course, an increasing process. If the split is such that there is a conservation of mass, so that we split so that the mass here is exactly equal to this one here, of course you will end up at the initial mass. But what you can do as well is, instead of splitting this in a deterministic kind of way, you can do this in a random kind of way, where on average you conserve the mass. So for example, if you have a fraction here m0 and a fraction here m1, you can do this split such that the expected value of m0 plus m1 equals 1. So on average you conserve this mass. Okay, so here your process m would increase from 0 to some random quantity. Okay, so to compute the multifractal spectrum of this using the multifractal formalism, and it's an example where equality holds everywhere, we need to compute this tau of q. Okay, but in fact, if you try to do the mathematics using the Holder exponent that I introduced before, you would be rapidly stuck. Okay, because remember what we're considering is 3 consecutive intervals, and this is not going to be very tractable when you try to raise everything to the power q. So what we're going to do is we're going to introduce another set of exponents which are defined like the HKN, except that we are considering increases over just one dyadic interval and not 3 consecutive ones. And because the process M is increasing, the supremum is of course taken as the difference at the right-hand point minus the value of the process at the left hand point of your interval. Okay, and in fact, if you use these exponents, or if you use these exponents, you can show that basically you end up with pretty much the same analysis in the sense that your T of Q computed using this alpha exponent is the same as the T of Q computed with this coarse exponent. So you can show that, okay? And so instead of working with this H, we're going to work with this coefficient here. So if we do this, we can compute things quite well. So there's many things that I should have introduced to finish this calculation, actually, but never mind. Okay, so basically this quantity here is the measure of your dyadic interval, IKNN. And if now we consider this dyadic structure, if we have a look at what is the actual mass of your subinterval AKN here, it's obtained as the initial mass where we are cascading weights along a line of descent. Okay, so if this corresponds to you IKN, here you've got weights, rho 1, rho 2, and so on, and that's your initial mass. The mass of AKN is m0 times rho 1 times rho 2. But this is if you only consider the upper half of the tree. But of course, it's more general than this because you need also some summary about the infinite tree that is below this point. And the mass of this tree that is below this point, I denoted by capital W, will have the same distribution as the mass of the full tree. We were considering infinite trees here, so I'm not saying it's the same, but it will have the same distribution. So that in fact, the measure of this interval is given by the product of all the weights. Let's suppose here we start with a mass, initial mass equal to 1. The mass of this interval is rho 1 times rho 2 times the summary of what is below this tree, so times this W here. And so this measure here is going to be equal to rho 1 times rho 2 times rho n. We are generation n, so there are n weights here, times this W n, which corresponds to the mass of the subtree rooted at this particular point. Okay, so now that we have this, what we need to compute is the expected value of the structure function. So the expected value of S alpha n q, which is by definition the expected value of the sum of all points, so the sum of all points which are at generation n, times what? Times rho 1 times rho 2 times rho n times r wn to the power q. This is exactly this quantity here. Okay, so now what we're going to assume is we're going to assume that we have independence between the weights. So the way we split is independent at each iteration, and independent on the right and independent on the left as well. So that because everything is independent here, this Wn here is independent of the rows as well. So this expected value is just going to be a product of expected value of row 1 to the q, expected value of row 2 to the q, up to row n, times expected value of Wn to the power q. Okay, and what we're going to assume even further, and that's the setting of the binomial cascade, is that each row, I, will be distributed like, or will be, yes, distributed like some row not if I is even, and some row 1 if I is odd. In other words, every time you split to the left, you split according to row naught, and every time you split to the right, you split according to row 1. So in this case, what is this value? Well, because you've got a dyadic structure, what we are really counting here is the number of times we split according to row naught and the number of times we split to row 1. So, how many ways can we choose out of n objects? We've got n generation. How many ways can we choose k fois row naught? We end up with the binomial distribution, right? So we've got expected value of Wnq times the sum for k equals 0 to n of n choose k times expected value of row naught k. To the power q, everything to the power k, times expected value of row 1 to the power n minus k. And this, of course, is equal to expected value of row naught to the power q plus expected value of row 1 to the power q. Okay, so that's for the expected value of the structure function. Now if you take the log minus 1 on n and you take the limit, you see that you end up with the following. You end up with tau alpha of q, which is equal to minus log 2 of expected value of row naught to the q plus expected value of row 1 to the q. And that's your partition function. So you see that for q equals 0, you end up with minus 1. And for q equals 1, if you have conservation of mass, you end up with the value 0. So in other words, you've got something which is concave. Okay, so we do have equality here. At 0, equal to minus 1. At 1, it's equal to 0. And you've got typically the tau of q, which look like this. And if you take the Legendre transform, you end up with a spectrum d of h, which is concave and looks like this. And this is typical to multifractal signals, multifractal processes. You end up with a spectrum which is concave with one particular Holder exponent here which has full dimension, and the rest of the points are fractal of dimension which is strictly less than 1. Maybe I should stop here. I guess that's a good place to stop. I could go on and talk to you about the self-similar with stationary increment, for which, for some of them, like the fractional Brown motion, we've got a linear partition function, and the spectrum degenerates to a single point. For example, the fractional Brown motion with index h has a single Holder exponent, which means that the partition function is linear, and when you take the Legendre transform, you end up with a single point. And here you end up with a signal which is known as monofractal. So I studied this kind of signals in my research, the spectrum, the partition function, and so on, and I wanted to introduce it, but maybe some other time. So, yeah, thanks for your attention.
We have time for some questions, and I will misuse my ability to moderate and ask a question precisely.
Yes.
So, what kind of signals do we have in the real world that have multifractal properties?
many. There's many different applications of this. For example, if you have a look at the heart rate as a time series, it has some fractal properties, and people have been looking at the estimation of the multifractal spectrum, which can actually detect irregularities for patients which are sick compared to healthy patients, depending on how rough the signal is. Financial applications, of course, many applications, the study of internet traffic data, but some more exotic application as well. One I like is in image processing as well, so you can actually look at the roughness of an image, for example. And it's been used recently by some people in Lyon to help to classify some paintings by Van Gogh. Because Van Gogh actually did paint in different ways, before a certain period and after a certain period. And some art experts really try to really know which painting corresponds to which period. But there are a few paintings for which it's not known. And so what they did is they had a look at the multifractal spectrum of these paintings. And they saw that depending on the period, the spectrum was shifted to the left or to the right. What does it mean? It means that depending on the roughness of the way he was painting, you've got very small order exponent because it's very rough. Or if it's shifted to the right, you've got higher order exponent, so you've got higher regularity. So it tended to paint in a different way. And so it actually helped for the classification of these paintings, for example. I mean, I think that's a nice application, but yes, it's used everywhere.
Questions?
Could you please comment why the maximum of d of h is achieved at 1?
That's generally the structure. That's really the structure. Yes, you've got one h for which you've got full Hausdorff dimension, which you're completely dense on the set 0,1, and the rest of it is just a dust of points which have a non-integer fractal dimension.
So is it always the case?
From the signals from the class of signals that I've been studying, yes. Is it true in general? Good question. For self-similar with stationary increments processes, yes, it's true. For multiplicative cascades, yes, it's true. But then after, if you consider multiplicative cascades which have a fractal support, then this will not be true. So instead of having support 0,1, you can actually consider fractal support here. And then it will not be true in that case.
And what about concavity?
Not always true. Not always true. Okay. Any more questions?
Thank you.
Okay, well, thanks, Gérard.